All right, Chemistry 3101. This is Chapter 5, which deals with the topic of stereoisomerism. So I'll probably switch back and forth between my slides and my camera a couple times today to show you a few things on some molecular models. So we're going to start off by reviewing isomers, because isomers is a concept that you would have been introduced to in general chemistry. And we looked at isomers also earlier on in this class in Chapter 2. We dealt with molecular representations, and we discussed then, we said, well, if we have isomers, we have something called constitutional isomers, which are molecules that have the same molecular formula, but they have a different connectivity of atoms. And the classic example that I used is a really simple one. If you have the formula C6 or C2H6O, you can either have this, which is ethanol, or you could have dimethyl ether. So again, the two molecules are made out of the exact same atoms, but they are different molecules, right? One of them is an alcohol and the other one is an ether. So these molecules have different physical properties, different melting points, different boiling points, different densities. They react differently. But in this chapter, we're going to be concerned with what are called stereoisomers. Okay, so this is a little more complex because we're dealing with compounds that have same molecular formula and the same connectivity. Okay, they do have the same connectivity. How do they differ? They differ in the spatial arrangement of atoms. And if you're wondering, what does spatial mean? Well, spatial just means the arrangement of the atoms in space or in 3 dimensions. And that's why molecular models are going to be very handy to have when you're studying Chapter 5. So if we take a look at an example of stereoisomers, it says here that although the two molecules that are shown here, we have these two 1,2-dimethyl cyclohexane derivatives. They both have the same connectivity, but they're not identical molecules, are they? Okay, now if we just examine both of these molecules, you can see that we have a 6-membered ring. We have a 6-membered ring. Good. Okay, we have a methyl group on 2 different carbons that are adjacent to one another. But the difference is that the 2 methyl groups in this compound are on the same side of the ring. And that's why we call it a cis compound, right? Because the 2 methyl groups are on the same face or the same side of the ring. If I look at the other compound, the reason we call it trans is because the 2 methyl groups are on the opposite sides of the ring. Okay? Now, in order to give these compounds a proper or unique IUPAC name, we have to have cis or trans as a prefix, right? Because there's a difference between these 2 compounds. There's no way I can flip a ring or change the conformation to go in between these 2 molecules. Impossible. Okay, their connectivity is identical. Yes, I agree with you. Okay, their connectivity is exactly the same. However, the arrangement of the atoms in space is different. Put another way, sometimes I like to imagine myself like being inside a molecule. I know it's strange, but come on, I've dedicated my life to organic chemistry. So imagine you're here, right, on this molecule. Imagine you're standing on this carbon. What you would see standing here is going to be different than what you would see here, right? So clearly, the way the atoms are arranged in space is different. And again, I know that you saw me when we looked at cyclohexane, you saw me do all kinds of ring flips with my model, right? There's no way that you can flip a ring and put 2 methyl groups that are on the same side of the ring and render the molecule in such a way that one of the methyl groups will be on an opposite side of the ring. Give me a thumbs up if you follow me on just that concept. Okay, that these molecules are different. Yes, they have the same molecular formula. Yes, they have the same connectivity. However, the arrangement of the atoms in space, their spatial arrangement, the 3-dimensional structure of the molecule is different in both cases. Well, I'm going to use my models for this example here. Remember we talked a lot about pi bonds a while ago? Okay, we talked about what constitutes a pi bond and why a carbon adopts sp2 hybridization way back in Chapter 1. Well, in order to maintain a pi bond, the carbon-carbon bonds cannot freely rotate, right? If you have a sigma bond between 2 carbons, let's say you have ethane, right? Very simple molecule. We know that there's free rotation around a sigma bond. However, there is not free rotation around a pi bond. So if we look at these 2 molecules that I have shown down here at the bottom, we get cis-2-butene and trans-2-butene. These molecules both have the exact same molecular formula. they have the same connectivity. What do you mean by connectivity? Well, if we look at these two carbons in the double bond, you see one of them is attached to a methyl and a hydrogen. Good, same thing here. And this one is also attached to a methyl and a hydrogen. Yeah, same thing here. So again, the connectivity, the way, the order that they are connected is identical. However, the arrangement of the atoms in space is different. Again, imagine yourself standing somewhere inside the molecule. If you were here or if you were here, right? What you would see is that two methyl groups are going to be closer together in the cis 2-butene than they are in the trans 2-butene. So I'm going to switch over to my camera for just a GIF here. Just give me a sec. Okay. So I've gone ahead and I've made, I always get that stupid light in the background. Anyhow, so I've gone ahead and I've made two models. I have a cis alkene, so you can see that these two atoms are on the same side of the molecule, and I've got a double bond. There is no way for me to rotate that double bond. Double bonds are rigid, okay? Now, here I have the trans below it. These are two different molecules. I cannot overlap them. You see that the white and the green are not overlapping, right? The same thing applies to the trans. I cannot rotate this molecule. There is no free rotation around a pi bond. And so what's our conclusion? Our conclusion is that these molecules are stereoisomers of one another. They have the same connectivity. However, they have a different arrangement of atoms in space. All right, give me a thumbs up if you follow me on that concept. Just the fact that these two alkenes are stereoisomers, nothing more than that. Anybody with me on that? All right, good, good. There we go. Okay. Well, with that in mind, let's see if we can identify some pairs as being constitutional isomers. So there's three options here. They can either be constitutional isomers, they can be stereoisomers, or they can be identical structures. Okay, so identical, stereoisomers, or constitutional isomers. Let's label the first one. We'll call these A, B, C, D, and E. We'll do it like that. Okay, so this is where it gets a little tricky, right? Because we have to be able to manipulate molecules in our mind. Now I'm going to ask you about A. Does anybody have an idea about A? Whether these would be constitutional isomers, identical, or stereoisomers? Yeah, Skylar says that they're the exact same molecule. Yeah. Does anybody agree? Yeah, they're identical, right? These two molecules are identical. Now we know that a ring can flip, right? But here the ring can flip, and here the hydroxyl is up and axial. And when the ring flips, the hydroxyl still has to be up. Here it's up and equatorial, okay? There's the hydrogen pointing down here and the hydrogen pointing down here. And so these are the exact same molecule, they're just flipped. Okay, good. All right, what if we look at B? Does anybody have a feeling about B? Would these be constitutional isomers, stereoisomers, or identical? Yeah, absolutely. Yeah, I see that some students are saying that these are stereoisomers. Yeah, they're just giving me the shorthand, stereo. Yeah, you're absolutely right. These are stereoisomers. So I'll write it here. These are stereoisomers. Okay. Why? Because you see that in this, the first molecule, you see that this hydroxyl is pointing up and this hydroxyl is pointing up, right? Both of these hydroxyls are on the same side of the ring. Whereas here in the second molecule, this one is pointing up and this one is pointing down. Now, the reason that nobody chose constitutional isomers is because these two molecules have the exact same connectivity, but what do they have? They have a different arrangement of atoms in space, right? Remember, these two hydroxyls are on carbons that are next to each other. What about C? Does anybody have an idea about C? And it's not a trick question. Yeah, absolutely. These are constitutional isomers, right? They both have the same formula, which is C5H12. So it's H10O, right? Both are C5H10O. But these definitely don't have the same connectivity, do they? So these would be constitutional isomers, right? That's a question I could have asked you on the first quiz, okay? What about D? Does anybody have a feeling about D? Let's see here. Yeah, okay. Good. Yeah, my students are definitely on top of things this morning. These two molecules are identical. Identical. If you don't believe me, this would be really handy to make a model. But if you were to take this molecule and grab it by this methyl group, and you were to, probably an easier way would be to do this. Imagine, and this is Mr. Dion's rendition here. This is my pancake flipper, okay? Make it flap. If you were to put the pancake flipper under here and then you were to flip it over, right, over like this, you'd end up with this molecule, okay? And so in this case, I'm just flipping it like a pancake, and you see that it is the same molecule. Okay, anyhow, and then the last one. What about this one, E? Does anybody have a feeling about this one? I think that most people are getting the hang of it. The last one, E. What would these be? Anybody have a feeling about E? Yeah, okay. So I'm seeing some people say that they're the same. These are different molecules, okay? Remember that there is no free rotation around a pi bond, right? There's no free rotation. And so if you look at this first molecule, you see that you have a hydrogen pointing up and a hydrogen pointing down. So you could say the hydrogens are trans to each other. And here the hydrogens are on the same side of the double bond. And so the hydrogens here are cis. So if you were to make a model of both of these alkenes, there's no way that you could interconvert those two. And what I think some students might be getting tricked on is that they might think, well, here there's free rotation around this bond, right? Right? They're saying there's free rotation around that bond. But remember, that bond is neither here nor there, okay? We're talking about the orientation around this bond, and you can see that it's clearly different in the two. All right, there we go. Does that clear it up a little bit? I hope so. Let's take a look at another example. It says identify whether these molecules are cis, trans, or neither. Let's go through these together. If we look at this alkene, we'll call this one A. In order for an alkene to be cis, we have to have two groups that are the exact same on the same side of the molecule. And so since we have two hydrogens that are on the same side, this alkene is a cis alkene. Here we have a cyclohexane derivative, right? We've got a hydroxyl that's pointing up and axial here. We've got a hydroxyl here that's pointing up and equatorial, right? If you were to draw that molecule in two dimensions, you would just draw this. You would draw this, and you'd put one of them pointing up, and you'd put the other one pointing up like this. And so this molecule is a cis molecule. We call that B. What about C? Does anybody have a feeling about C? And it's not a trick.
Would it be trans?
Yeah, they're trans because the two hydrogens are identical groups and they're on opposite sides of the double bond. And so this is a trans alkene. Over here in D, we have a trans diol, is what we call when we have two alcohol groups in the same molecule, called a diol. So this would be trans because they're on opposite sides, right? This one is pointing up, this one is pointing down. And what about E? Would this be cis or trans? Could you define E as cis or trans? The answer for E is neither, okay? It's not cis and it's not trans. And there's a rule of thumb that you can invoke here, okay? If you have two methyl groups, okay, that are two groups that are the exact same on one carbon, okay, you can't have cis or trans. It's impossible, right? Because you have a methyl group here. These two groups are trans to each other, but these two groups are cis to each other. And so it's neither cis or trans. So again, on one of your carbons in the double bond, if you have two groups that are identical, there's no such thing as cis or trans for that molecule. It won't exist. Okay? There we go. All right. Well, let's move on to section 5.2, which is where we really turn up the heat. Okay? So it says here cis-trans isomerism is only one type of isomerism. There are many other important stereoisomeric relationships. In this course, we kind of just go over the most important ones. It's a broader subject than what we learn in Organic Chemistry 1. But anyhow, in order for us to be able to identify stereoisomers that aren't just cis and trans isomers, we have to be able to identify what a chiral molecule is. So it's not chiral, it's chiral. A chiral object is something that's asymmetric, which simply means it's non-superimposable upon its mirror image. Okay? If you take a look at the example that's shown down here, we have this pair of John Lennon glasses, so to speak, and you can see that this pair of glasses is superimposable upon its mirror image. So it is not chiral, and we say that it would be achiral is the word that we use for that, okay, which means it's not chiral. However, if you poke one of the lenses out, right, and if you were to try to overlap these glasses, okay, or maybe I should use a black pen here. If you were to try to overlap these glasses with these ones, what would you see? You'd see that the shaded in lens would end up over here. And so these were not superimposable. And so the pair of glasses with the lens poked out is in fact a chiral object, okay? Again, it's just like our hands, right? If you take your left hand and your right hand and you put them side by side, they're mirror images. However, if you try to lay them on top of each other, you see that your thumbs end up on opposite sides, and so they are not superimposable. Chirality is really important to molecules because it says here that if two chiral molecules are mirror images, they are going to have many properties that are identical. Okay, they're going to have the same boiling points, right? If we go identical properties, they're going to have similar or the same things like boiling point, melting point, density, etc. And the reason why is because those physical properties are a result of the structure of the molecule, okay? So if the structures are the same but just mirror images, the molecules are going to interact with each other in the same way. But because they're not identical, their pharmacology is going to be very different, and that's important because our bodies are chiral, okay? The receptors on the cells in our body are chiral. So we'll put here bodies, so to speak, okay? Bodies are chiral, or the environment, okay? In our body, the biochemical environment in our body is chiral. So an example of this would be the thalidomide. I'm sure that you've all, probably most of you have heard of the thalidomide drug, which was administered to pregnant women in the 1960s, and it was sold as given to patients in order to alleviate morning sickness, and this drug was given as a mixture of two mirror images, right? You had two chiral molecules, but they're mirror images, so same melting points, same boiling points. The thing is that one of the mirror images was able to alleviate morning sickness. However, the other one was, it's called a teratogen, and it caused birth defects, severe birth defects. So chirality is really important. Anyhow, visualizing mirror images is not simple. Okay, it's not trivial. It can be challenging for some students. Some students seem to get it right away, especially students who are used to maybe working on models or car engines, because you're used to looking at, you know, paper, which has a 2D engine, then you look at it in 3D, so on and so forth. Anyhow, and so I would recommend if you're really struggling with the concepts and the subject, it might be a good idea to buy a molecular model kit. If you look in the syllabus, you see that the kind that Dr. Anderson and I recommend are the HGS brand. You can buy them. I checked it out on Amazon. It's around $20 to buy a kit of molecular models, which are really nice. Anyhow, really nice models. Anyhow, so how do we know that we've got chirality, right? Is it always going to be like a pair of sunglasses, like John Lennon's glasses? No, no. Chirality most often is going to be the result of when we have a carbon that's bound to 4 unique groups of atoms. Look deep into my eyes. If you're not paying attention, wake yourself up for the next 10 seconds, okay? Not unique atoms. Unique, starts with G, ends with groups. That's right, groups of atoms, okay? Groups. So we can have 4 carbons attached to a carbon, but if there are 4 different groups, that renders the carbon chiral. So if we look at this carbon here, you can see that it's attached to 1, 2, 3, 4 different groups, right? All 4 different colors. Here's the mirror image of that molecule. And those 2 models are not superimposable upon each other. I'll prove it to you. So if I go, how do I get back to my camera here? Stop broadcasting. All right, give me a second here, and I'll prove it to you, right? Show, don't tell, right? Anyhow, so you can see that this molecule that I just made is chiral. This carbon is attached to 4 different groups. Now let me try to orient this one in the right way. If you look at this molecule, Okay, there we go. Son of a gun. There, that's better. Okay, you can see that these are mirror images of each other. However, they are not superimposable. They'll always line up with two of the atoms lining up, okay? But you can see that the blue and the white do not line up. And if you're thinking, oh, Mr. Dion, you're just not holding them in the right way, you need to orient them in a different way, and then they're going to overlap. Well, the answer is no, they won't, okay? I know they won't. I can prove it to you right here. So look, now the blue and the orange overlap, but the yellow and the white don't, okay? And there's, I promise you that that will work all the time. Okay. Again, if you don't believe me, make a model and you can prove it to yourself. Even if you only have something like Tinker Toys, that might work to make a molecular model. So if you look at this molecule that's shown here, right, because we're going to be interested in molecules and not just carbons that have spheres attached to them, you can see that this carbon is chiral. Why? Because it's attached to 4 different groups, right? We have this hydroxyl, we have a hydrogen, we have a methyl, and we have an ethyl, right? 4 different groups, okay? If you look over here, you can see that this carbon is chiral. Oops. This carbon is chiral. It's attached to 4 different groups, 1, 2, 3, 4, and you can see that they're mirror images, and therefore these are stereoisomers of each other. Well, how do we describe those? We're going to get to that in a second, but let's talk a little more about chirality. When an atom, like carbon, has a tetrahedral center, so sp3 hybridized, with 4 different groups, it's called a chirality center. Sometimes we call it a chiral center or a chiral center, or sometimes it's called an asymmetric center, right? Organic chemists love to have more than one way to describe everything to make themselves feel good, right? Anyhow, so analyze the attachments for each carbon or each chirality center below. So we have 3 chirality centers that are highlighted in green, okay? Why is this first carbon chiral? Why is this a chiral carbon? Because it's attached to a chlorine, an ethyl group, a methyl, and there's also a hydrogen atom right in the back. So we have our 4 different groups. Therefore, that's a chiral center. The next one, this carbon is chiral. Why? Because it's attached to an ethyl group, a propyl group, a hydroxyl, and there is also a hydrogen in the back. This one is a little bit trickier. Let's start by drawing our hydrogen that's in the back here. And hopefully you can see that this chiral, or this carbon is chiral because it's attached to a bromine, a hydrogen. Look at this carbon. Are these 2 carbons identical? The answer is no. We have a CH here and we have a CH2 here. And so these 2 are different groups. And so that is a chiral carbon. All right. Anyhow, there we go. So we have a chiral carbon. You know, if you're wondering, well, what about all the other carbons, Mr. Dion? Why isn't this CH2? Why isn't this carbon chiral? Right? Not chiral. Could anybody tell me why that CH2, that methylene, is not chiral? That's exactly right, Byron. It's because it's got 2 hydrogens attached to it. So whenever you have a methylene, it's impossible for it to be chiral. And if you have a methyl, it's impossible for it to be chiral. So always achiral. No exceptions. All right, here we go. Let's identify how many chirality centers are in each of these molecules. If I label these A, B, C, and D, could anybody tell me how many chirality centers are in A? It might not be easy, but you can give it the old college try. And I'll give you a clue that 0 is a possible answer. How many chirality centers would there be in A? Kayla says none, and I tend to agree with you that there's no chirality centers in the first one, right? It might be a knee-jerk reaction to say, well, this carbon's chiral. Well, hold the phone. It's attached to a hydroxyl, a hydrogen. You've got a CH2 and a CH2 here. Okay, those are identical. You've got a CH2 here. Those still identical. And then they meet down here at the middle. And so since the pathway, whether you go this way or whether you go this way, is identical, there are no chiral centers in A. What about B? Would there be any chiral centers in B? Yeah, in B, thanks, Byron. There are two chiral centers in B. Oftentimes we denote a chirality center with a little star, a little asterisk or something. So we have a chirality center here, and we have a chirality center here. And if you're thinking, come on, Mr. Dion, there's a plane of symmetry down that molecule. Well, hold the phone. If we examine this carbon first, you can see that it's attached to a hydroxyl. It's also attached to a hydrogen. Now remember, it's 4 different groups. If you look at this carbon here, this carbon is attached to a hydroxyl, a hydrogen, a methylene here. That's different than this carbon here, which is just a methylene, right? What I'm saying is this carbon is different than this one. And so the carbon that has the blue asterisk on it is chiral. It's attached to 4 different groups. And we would use the exact same rationale to prove why the carbon with the red asterisk is chiral. We'll do it a little quicker. It's attached to this hydrogen, this hydroxyl, this carbon, which is different than this methylene here. And so we have 2 chirality centers. So the first one was 0. The second one is 2. What about C? Does anybody have an answer for C? I'm gonna have to speed it up a little bit after this. Yeah, the answer for C is that there's 2, okay? We have a chirality center here, and we also have a chirality center here. This is not a chirality center. Why? Because this is a methyl group, and this is a methyl group. So since this carbon has 2 groups that are identical attached to it, it is not chiral. If we examine the one with the red asterisks on it, you can see that it's got a hydrogen coming out in front. It's got a methyl group here. So look, we've got a methyl group. We've got a hydrogen. We've got all this spinach over here, which is a sec-butyl, and then we've got an isopropyl over here. Those are 4 different groups, my friends. So that carbon is chiral. We'll try the exact same exercise with the carbon with the blue asterisks on it. We've got a hydrogen going in the back, right? We've got the methyl group over here. Let's take a look. 1, 2. We've got an ethyl group here, and we got all this spinach over here. So those are definitely 4 different groups. Remember, not 4 different atoms, 4 different groups. And so the answer here is 2. Okay. The next one has 2 chiral centers. We've got a chiral center here, and we have a chiral center there. Carbons attached to 4 different groups. And make sure you take a look at that one. But I want to keep moving and ask you to identify. This one's tough to do over Microsoft Teams in class. I would usually put it up on the, project it on the screen and ask my students, how many are there? Where are they? And students would point them out. Does anybody have an idea, or did anybody try this one ahead of time? How many chirality centers are in here? You got to kind of dig around, or could anybody identify one of them, or just describe one of them to me? There's one that's pretty describable, I would say. Okay, yeah, it might be tough to answer that one over Teams. Anyhow, you can clearly see that this one is a chiral center, right? It's attached to the hydroxyl. It's also attached to a hydrogen. You've got CH2 with a quaternary carbon here, and then here you got CH2, CH2. So those are clearly 2 different groups. The other ones, and again, I want to keep moving here just in the interest of time, and there are 4 more of them. There's a total of 5 in this molecule. We have one here at this ring junction. We have another one here at this ring junction. There's another one here, and the last one is this one right here. So make sure you take a look, and if you look at this, practice the skill, there's a question, I believe, just below it, I think, or maybe it has some other questions that ask the exact same thing. They give you a big molecule, that you would never be expected to understand the reactivity or the name of, but they just want you to be able to look at it and say, okay, well, this is a chiral center and this isn't. And when you practice it, you'll train your eye to recognize chiral centers pretty quickly. Well, let's talk about what an enantiomer is. If you read the book, you surely saw the word enantiomer come up over and over and over, because you remember when we talked about the John Lennon glasses, or the 2 molecules that I showed you, that I had made the 2 models that were non-superimposable mirror images? The technical term for those is enantiomers. Okay, so enantiomers, says below, are just 2 molecules that are mirror images, but not superimposable. So they're not the same molecule. Okay. Only a chiral compound can have an enantiomer, so you've got to have at least one chiral center in your molecule in order to have an enantiomer. So how would you draw the mirror image of this chiral compound here, right? You can see that this carbon is chiral, okay? So how would I draw the mirror image of that? Well, you can kind of think about it in your head. You say, okay, I'm going to start going backwards like this, draw my 4 carbons, and then I'll do this like that. And those are both mirror images. There's nothing wrong with what I've drawn here. The relationship between these two molecules is that they are enantiomers. However, there is a much faster way to draw an enantiomer, and that is to draw the same carbon skeleton, the exact same thing, but anything that's got a chiral center on it, if it's a wedge, you turn it into a dash, and if it's a dash, you turn it into a wedge. Okay? So if I take this wedge and I turn it into a dash, these two molecules are enantiomers of each other. Okay? So these are enantiomers in, we'll just say En, and then these two molecules are enantiomers of each other. And you can see that just inverting a dash or a wedge is a lot simpler than actually trying to draw a mirror image. I mean, especially when you get into molecules that have multiple chirality centers, it would get really, really difficult. Okay, and here's a slide summarizing what I just told you. It says another easier way to draw enantiomers is just to invert or swap or switch, whatever you want to call it, dashes and wedges. Here we have a wedge, you turn it into a dash, my friend, and you've got enantiomers. Here we've got, this is amphetamine. We have a wedge here, and so we make a dash here, and there you go, the two enantiomers of amphetamine. Now, if you look at this compound here on the bottom, it says, you know, you drew this bond with a wedge here, with a dash here. However, these are the same molecule, aren't they? These are not enantiomers. Why would that be? Now, I know you know the answer, so I'll say it pretty quickly, but it's because the carbon that has the wedge or the dash drawn on it is not chiral, right? They're both attached to 2 methyl groups, and so those are not chiral, okay? Not chiral compounds, so those are not enantiomers. So we can put here identical. There you go. All right. Well, if one compound has a dash and another compound has a wedge, okay, how do we describe the difference between those molecules? You don't say, pass me the wedge, 2-chlorobutane. Pass me the dash, 2-chlorobutane. No, we have a much better way to designate the difference between the chirality centers or the asymmetric centers or the chiral centers, whatever you want to call it. Again, enantiomers are unique. They're different compounds, so they must not have the same name. So how do we denote the difference between these compounds? We use what are called the Ingold Prelog rules, or the Ingold Prelog system. Sometimes you'll see it just abbreviated, the CIP, like that. Anyhow, it's developed by these 3 scientists, and we designate the chirality of each center as having R or S configuration. Now, this is going back in time here, but I think R stands for rectus, okay? And then S stands for sinister, okay? And if you're a left-hander like me, then you know what sinister means, right? Sinister means left, okay? It means left-handed or going to the left, and rectus is Latin, I believe, for the right-hand direction. So R stands for right, if you will, and S stands for going to the left, okay? Another way you can think about it is that right stands for going clockwise, and S is when we're going counterclockwise. And if you're like, clockwise what, counterclockwise what, Mr. Dion? Hold on, I'll explain it. Let me show you. Here are the rules, right? Science students love rules, and organic chemistry is replete with them. How do you assign a chiral center as being R or S? Now, if you're confused with what the hell I'm talking about, what I'm saying is that each of these chiral centers, they're either R or S. So this is R or S, and the same thing with this is on this R or S, and we're trying to figure out which is it. So let me show you how you do that. Okay, using atomic numbers. Okay, so the numbers on the periodic table, right? Nitrogen has an atomic number of 7. Oxygen has an atomic number of 8. So using atomic numbers, the 4 groups attached to the chirality center, you're going to prioritize them 1, 2, 3, 4. The group or the atom that has the highest atomic number is going to be the highest priority, okay? the atom with the lowest atomic number is going to be the lowest priority. So, for example, if you have a hydrogen, it's always going to have a priority of 1, right? It's always going to be the loser, the lowest, or sorry, 4. It's always going to be the lowest priority. That's if you've got a hydrogen, and we're going to see that a lot. Then what you do is you arrange or orient the molecule in space in a way so that the lowest priority group, which again, oftentimes in this class, not always, but probably like 80% of the time, or 70% of the time, it's going to be hydrogen. You put that so it's facing away from you. So you put that at the back, okay? At the back. And then you count the other groups around the chiral carbon in order, 1 to 2 to 3, and you determine whether you're going in a clockwise or counterclockwise direction. If you're going in a clockwise direction, the stereochemical configuration is R, and if you're going in a counterclockwise configuration, the stereochemical configuration is S. Again, if you use a handheld model, it can be handy to do this. If we were in Centennial Hall, I'd show you some other funny things that I see students do from time to time. I'll even see students like pick up a piece of paper and hold it on its edge, which doesn't change anything. But in your mind's eye, it can change things. So I don't laugh at students that do that. I've done it myself. Okay, so let's say we had this molecule right here. You know what? Let's go back to these. Let's go back to these ones. And I'm going to erase this and show you how to do it before I show you the example. Okay, so let's say we wanted to do this molecule here. On the left, you've got a hydrogen in the back. Okay. All right. So we've got a chlorine, we've got a hydrogen, we've got a carbon, we've got a carbon here, and we also have a carbon here. Okay. So here it doesn't look like we've got 4 different groups, but what is this carbon on the left attached to? It's attached to 1, 2, 3 hydrogens, and this carbon is attached to 2 hydrogens and a carbon. If we make a laundry list and we list these 3 atoms, right, we have hydrogen, hydrogen, and hydrogen. And if we list the 3 atoms that are attached to this carbon, we have carbon, hydrogen, hydrogen, because we list them in order of atomic number. Since carbon has a higher atomic number than hydrogen, that means that this carbon is going to have a higher priority than this one. Okay, so the highest priority group is going to be the chlorine. It's got an atomic number of 17. Hydrogen is going to be the loser. This one is going to be number 2, and this one's going to be number 3. Here's my chiral carbon. I'm going to do the dance going around the chiral carbon. I'm going to start on the first priority. Then I'm going to go to the second priority. Then I'm going to go to the third. So look, I'm going around the chiral carbon. Which direction am I going? Am I going clockwise or counterclockwise? I am going clockwise, and so this carbon is R, right? Because I told you that having a clockwise configuration is R. Now let's look at the example that's shown here. This is normally the example that I use first because you got 4 different atoms, but let me show you something interesting that occurs with this molecule, okay? You use atomic numbers to prioritize the 4 atoms that are, or the 4 groups that are attached to the chirality center, right? Chlorine has the highest atomic number, oxygen is second, carbon is third, and the proton or hydrogen is fourth. All right, so we're good on that. The problem is that, remember I told you that the second rule was to arrange the molecule in space so that the lowest priority group is facing away from you? Well, damn it, in this molecule, the lowest priority group is coming towards you, right? It's facing toward you, coming straight for us, okay? So what do? Well, there's a couple of approaches. Now, what it says in our book, it says to rotate it, to spin it around. So if you rotate it around this axis, okay, that's shown right here, you would swap the 1 and the 4 and the 3 and the 2. Then, after you've rotated it, you see that you go from 1 to 2 to 3 like this, which is counterclockwise. And so, therefore, it would be S. This is something I'm not a fan of, okay? Is doing it that way. Okay, so this is the conclusion that we just reached. So here's what I like to do, okay? And Dr. Anderson would teach you the exact same thing. If you rotate the molecule in your mind, I'm telling you, that will oftentimes lead to my students making mistakes. I don't like to see my students make mistakes. So there's an easier way. And if you're thinking, is it just for organic chemistry 1? Hell no. Okay, you ask any chemist who works her or his entire life doing chemistry, we all use this trick. And that is, if the lowest priority group is facing towards you, okay, so since the hydrogen is coming towards us, what we do is this. We go from 1 to 2 to 3, like that, okay? Like this, we go from 1 to 2 to 3, like that, which is clockwise, right? Which would be R, but we just switch it. So since this group is coming towards you, you're going to switch that, and it just becomes S. Okay, so you just swap it out. All right, and that's the easiest way to do it. All right. Now, again, what if you have two carbons? Okay, like I showed you in that first example. It says when the groups attached to the chirality center are similar, it can be tricky, but there's a rule, and it involves making that laundry list that I showed you a few minutes ago. Here is our chiral carbon in this molecule. Okay, what are the four groups that it's attached to? Look, if you just take it at face value, right, going right back to the beginning when I said, what's a chiral center, you guys? Everybody who's hearing the sound of my voice would have said, well, this is chiral, okay, because I have this hydrogen, I have this hydroxyl, I've got all of this spinach here, and I've got this sec-butyl group, right? So everybody would have said, yeah, that's chiral, that's cool, Mr. Dion, no problem. But what is this stereochemical designation? Is it RS? Then it gets more complex, okay? Give me 1 second here. Okay, no. All right, anyhow, so we have the oxygen, which is the highest priority, right? Oxygen has an atomic number of 8. Good. Then we have the hydrogen. It has the lowest atomic number possible, so it's going to be group number 4. If you look at these two carbons, okay, this carbon and this carbon, you make these laundry lists going away from the carbon. So if we go away, we've got 2 hydrogens attached to it and a carbon, right? Same thing here. We've got 2 hydrogens attached to it and this carbon right here. So we have CHH, CHH. There's no difference. So we keep going. You just keep going until you can find a difference. Excuse me. We move out to the next carbon. You can see that this carbon is attached to a carbon, and it's also got a hydrogen attached to it. Here's my laundry list. We go to this carbon. It's attached to a carbon, a hydrogen, and a hydrogen. So we make that list. And again, we order them with the highest atomic number first. Okay? The first 2 are the same. Here's the tiebreaker. Carbon is higher than hydrogen. And so that means that this group here has a higher priority. So that's going to be group number 2. Now to finish it all up, I'm going to erase some of my spinach here. Okay? To finish it all up, look, we're going to go from 1 to 2 to 3. So we go from 1 to 2 to 3 like that. We're going counterclockwise, which would be S. But since the lowest priority group is coming out towards us, we will switch it. So this one must be R, like that. Okay? Again, when you're doing this laundry list thing that I call it, okay, the priority is based on the first point of difference, the tiebreaker. It's got nothing to do with adding up atomic numbers or making a spreadsheet or getting a graphing calculator or a mainframe, or sometimes students try to turn it into something more complex than it is. I'm not saying that it's simple. Okay? Organic chemistry is not a simple subject. But if you look at this carbon here and this carbon here, what is this carbon that's on the left attached to? It's attached to this oxygen, right? And it's also got the 2 hydrogens attached to it. Okay? What's this carbon attached to? It's attached to 1, 2, 3 carbons. 2, 3. So what's the tiebreaker? The oxygen has a higher atomic number, and so this group has a higher priority than this group over here. Give me a thumbs up if you're even 70% of the way with me. Not a simple thing. Organic chemistry is not a simple subject. I'd be the first guy to admit that. Okay? But even if you're like, yeah, I think I get it, Mr. Dion. Yeah, it takes some practice. It absolutely takes practice. There's no doubt about it. But you can imagine that on your next quiz, I'm going to ask you more than one question where I simply ask you, what's the chirality of this center? Is it R or is it S? And you'll have to be able to say, well, this one's R and this one's S, right? as one of my students said, I have a 50-50 chance, you know. Well, it's better to know it than to have just go in there with just hoping for a 50-50 chance. Anyhow, if we take a look at this carbon here, okay, if we're making our laundry lists, okay, we have a carbon here, a carbon here, a carbon here, and then we have a carbon here. The way you do it when you have a double bond, the double bond counts like 2 bonds to an oxygen. Or, sorry, the double bond counts as 2 bonds, okay? Say, for example, you had a carbon and it had a triple bond to carbon like this, and you were making the laundry list for this one, right? And say this was a chiral center here. This carbon would be attached to carbon, carbon, carbon. So you'd say carbon, 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 okay? And if you're like, oh, I'm not 100% sure, Mr. Dion, again, when you look at many, many practice problems, which is really the only way to master this, you will you'll see examples with triple bonds in it too. Okay. Again, other tricks. I had a student of mine who wrote the MCAT, I don't know, a number of years ago. He just got accepted into medical school. He's going to start soon. But he came into my office one time and he said, hey, Mr. Dion, did you know that there's a trick that if you switch 2 groups on a chiral center, that it switches the stereochemical configuration? I said, yeah, I knew that. I taught it to you in class. You know, he just laughed. Anyhow, so he read it in the MCAT study guide or something. I was like, I guess you were asleep in that part of class. Anyhow, so just other little tricks that you can use. If you swap any 2 groups, it wouldn't matter if you swapped those 2 or these 2 or these 2 or these 2, whatever. If you swap 2 groups on a chiral center, you reverse the stereochemical configuration. Okay, so that's one little trick. Here are the summary for the Ingold Prelog rules. This is, again, comes straight out of the David Klein canon, you know, out of his textbook. If you want to read this a bunch of times and try to memorize it, you could do that, but I think the best way to do it is just practicing. So with that in mind, let's take a look at this molecule right here. Does anybody, well, you probably don't recognize this molecule. It's called L-Dopa. This is L-Dopa or L-Dopamine. Anyhow, I'm not worried about the name of the molecule, but you can see it's got a beautiful, tasty chiral center in it, doesn't it, right? Let's analyze this chiral center and determine whether it's R or S. Well, we've got a hydrogen coming out here. Okay, so that's going to be priority number 4. I have a nitrogen, I have a carbon, and I have a carbon. So the nitrogen is going to be priority number 1. Okay. Now, if I'm just going to throw this out there to my students. I don't think I've done this very often, but I'm going to throw this out there. If I circle these 2 groups, if I call this group A and call this group B, which is just something that I came up with, does anybody have an inkling which one of those would be higher priority? Like, would it be the carbon on the A side or the carbon on the B side, based on what I taught you so far? Which one would have a higher priority? Yeah. Good. Great. Good answer, you guys. Okay. If you're not sure, let me explain it to you. The reason why students answered that pretty quickly is because they said, well, look, Mr. Dion, this carbon has got a double bond to oxygen and a single bond to oxygen. So it's attached to OOO, right? Just like, what's that song? Paula Abdul, straight up, OOO, right? Anyhow, you have this carbon here. It's attached to a carbon and 2 hydrogen. So its laundry list would be carbon, hydrogen, hydrogen. What's the tiebreaker? The oxygen is the tiebreaker. I'll even write that in there, tiebreaker. Okay, so that means that this group has a higher priority. So next to this carbon, we'll write number 2. Next to this one, we'll write number 3. Follow the dance. The dance is a dance around the chiral carbon. And the reason I feel like, oh, Mr. Dion, you're so silly. Okay, if you're wondering why I say that, it's because I've seen some students try to do some things where they were trying to take these alternate routes or something. Anyhow, if we follow the path, look, let's go. We go from group 1 to group 2 to group 3. We are going in a clockwise direction. Now, clockwise, right? We said that we said that clockwise means that it's got an R stereochemical designation. But remember, this group is in front, and so we reverse it. And so the stereochemical configuration of this carbon is S. It's S. Give me a thumbs up if you follow me on that one. You're going to be asked to do that a few times on your next quiz. Is this R? Is this S? Cha? No? Good? All right. Great, as we say in whatever, Scottish. All right, anyhow. Let's see here. The RRS configuration is used in IUPAC nomenclature to distinguish enantiomers. So let's say you have these two butanols. One is R, one is S, right? And you're going to get so fast at this when you practice this. Look, you're going to go, look, come on, you guys. This is going to be group number 1. This is going to be group number 4. And ethyl is going to take higher priority over a methyl. We saw that already today. So this is 2. This is 3. I'm going like this. 1, 2, 3. That's counterclockwise. Or sorry, that's clockwise. That's R. All right? You're going to be able to do it really quick. All right? If you look at the first chiral center here, we number these atoms 1, 2, 3, 4, 5. Okay, you see that at carbon 2, we have an R stereochemistry, and at carbon 3, we have an S stereochemistry. I'm going to let you try this one to make sure that these are correct. I'm 99.999% sure they are. Okay, since I copied it from the textbook. But anyhow, all right. There's always mistakes in textbooks, right? Okay, let's see here. And let's talk. Give me a thumbs up if you're with me so far. What you've learned this morning, what we've covered, is not simple, right? Nothing in organic chemistry is, but it's important, and it's going to come up over and over again. Also, if imagine yourself being an instructor. Imagine yourself being the kind of person who writes MCAT exams for a living. Okay, you're a doctor, and they kick you out of the hospital. So you're like, I'll just make up MCAT exam. I'm teasing. Okay, but anyhow, let's just say you did something like that. You can see how stereoisomerism is a great subject, very easy subject to write questions about, right? All you have to do is give the students a molecule and say, is this stereocenter R or S? And leave it up to the students to figure it out their own selves, right? That's so you're going to be, if you're the kind of student, and I know I have many students in this class, or at least a few who are interested in maybe writing an MCAT exam or a PCAT exam or whatever. And you can be sure that in those exams that stereoisomerism is going to show up, right? Chiral centers have to be designated. Okay, anyhow, let's talk a little bit more about enantiomers, and let's discuss what's called optical activity. Now, optical, and you're like, what do you mean? We're going to the optician? We're getting a new pair of John Lennon glasses because we broke them? No, not exactly. Okay, let's take a look at these two compounds. We got R carbone and S carbone, which have very different odors, by the way. It's really interesting. Again, since the receptors in your nose are chiral, they would recognize the two molecules very differently. Anyhow, where the hell was I? Because the structures here are enantiomers, only differ in the way your right hand differs from the left. They've got the same physical properties, right? I went over that with you today. They've got the same melting point, same boiling point. If you were to run an IR on these compounds, right, they're going to have the same, they would have the same IR. Later on in this semester, in the beginning of April, we're going to look at a chapter that deals with what's called nuclear magnetic resonance spectroscopy. So that's called NMR. These two compounds would produce the same NMR. And again, you'll learn more about that later. Same mass spec, right? So same mass spec. So you're like, well, how in the heck would I differentiate between these? How would a scientist know? What do they do? Go around smelling everything? No. The way that you differentiate between two enantiomers is based on the fact that these two molecules are going to interact with light differently. Okay, so they have a different optical activity. Okay, they also interact with other chiral compounds differently. That is not really covered in this class. If you take organic chemistry for chemistry majors, we talk about that in that class, but not in this class. If you're wondering what's optical activity, well, I want you to make sure that you read section 5.4 before class next or this coming Friday, but I'm going to explain it to you pretty quickly here. Has anybody here seen fancy plain polarized sunglasses that you could buy and they have a little hang tag on them with a polarizing filter on it or another polarized lens? I asked my students the other day in a different class and they said, yeah, sometimes Oakley sunglasses. Has anybody seen these? You get a little hang tag on them and then you can rotate the hang tag. No? Okay, anyhow. Nobody's bought a pair of Coco Chanel's or something recently. Okay, maybe Jonathan has, Okay. Anyhow, the way that you know that you have polarized sunglasses is by taking that polarizing filter and rotating it in front of the lens, okay? If you're not sure what I mean, you could Google it and look up polarized sunglasses, which aren't cheap, okay? But anyhow, what we do is we take light, right, which is electromagnetic radiation, which travels in all planes, okay? So if you have just regular light, it travels in all planes perpendicular to the direction of travel. However, when you pass it through, this is called a polarizing filter. It only allows one of the directions of the light to come through that filter. So you filter out the other ones that are not aligned with the polarizing filter, okay? Now, if you shine that polarized light, so this is polarized light here, if you shine that polarized light through another polarizing filter and you have it aligned with the first one, the light's going to pass through it. However, and this is what you can do with those fancy sunglass tags, if you rotate the tag, you'll see that no light passes through, and that's how you know that you've got polarized sunglasses, okay? Well, what happens is we can take advantage of this plain polarized light, okay? Because we can take that plain polarized light and we can pass it through a solution of an organic compound, one enantiomer or another, and it's going to affect the direction in which the polarized light is rotated. And we call that compounds that are able to do that, we call those optically active compounds. And chiral compounds possess the ability to do that. So if you're like, not 100% sure what you meant, Mr. Dion, okay, what we do is we take a light source. It's a very specific light source. It's the D line of sodium, which has a wavelength of, I think, 589 nanometers. You shine it through a polarizing filter, right? I told you that light travels in all directions perpendicular to the plane of travel. Then when you pass it through the polarizing filter, you only get one direction of the light. Then you shine it through the light, the polarized light, through a polarimeter tube. Inside that polarimeter tube, you've got a solution of a chiral compound, let's say, chiral compound. And what that's going to do is it's going to rotate the plane polarized light in a direction. Now here they're showing it being rotated in a certain way, and then the person on the other end, with their eyeball, okay, looks through another polarizing filter, and then they adjust that polarizing filter to the right or to the left so that they can see the light shining through. Once they can see the light shining through, they know that they've rotated this lens to the same degree as the compound rotated the plane polarized light, and they can get what's called an optical rotation. So what you really need to know for this class, and this will probably come up on your final exam, is that enantiomers are going to rotate plane polarized light to equal degrees, but in opposite directions. Okay? Let me back up and let's look at two enantiomers. Okay? If you look at these two enantiomers, R carbone and S carbone, I really don't know what their optical rotation is off the top of my head whatsoever, but I'll just make up a number. Okay? If this one was to rotate plane polarized light by positive 40 degrees, this one's going to rotate it by negative, not degrees Celsius, like a temperature on the brain. That one's going to rotate it by negative 40 degrees. Okay? If the first one rotated it by negative 40 degrees, then this one's going to rotate it by positive 40. Okay, so it's just equal and opposite. I'm going to erase these because they're probably definitely not the right values. But that's all it is. So let me give an example of a very simple question that's shown up on the ACS final, okay? The national standard, okay, for this class is they'll give you two enantiomers. They'll say, this enantiomer rotated plane polarized light positive 19.3 degrees. The enantiomer will rotate plane polarized light, and they give you a bunch of answers, and one of them is negative 19.3 degrees. That's all it is. Nothing more than that. Enantiomers rotate plane polarized light in opposite directions. Okay? So I'm not going to talk about this right now, but when we report an optical rotation, which we denote an alpha, we also report the temperature and the wavelength. The wavelength that you're going to see in this class is always going to be D. And you're like, why the hell is the letter D a wavelength, Mr. Dion? It represents 589 nanometers, okay? So again, you can read more about that, but here's a perfect example of what I was talking about. Here we have the R and S2 bromobutane molecules. Look at what they do to plane polarized light. One rotates it negative 23.1 degrees. The other one rotates at positive 23.1 degrees. Okay? Now, if you're not paying attention, wake up again. Take a big drink of coffee. Okay? Big drink. What do you drink? Monster. What's another one of those drinks that students like? Red Bull? Is that still a thing? Anyhow, I don't know. Espresso? Starbucks? I don't know. But hear ye. Look deep into my eyes. Okay? And I'm going to tell you something that is 100% true. And you need to know this because I've seen students try to connect the dots between R and S and plus and minus rotation. If a compound is R or if a compound is S has nothing to do with whether it rotates plane polarized light positive in the positive direction, so it should be clockwise, or negative, which is counterclockwise. They are not related to one another. You can have an R compound that rotates plane polarized light negatively and an R compound that rotates it positively. The direction that a compound rotates plane polarized light depends on a whole holy host of factors. Okay, it even depends on temperature. Look at this. Okay, when we have positive rotation, we call that dextrorotatory, which means to the right. When we have negative, we call that levorotatory. I will use those words, dextrorotatory and levorotatory. But look at this chiral compound right here. The compound is levorotatory at 20 degrees Celsius. You jack up the temperature to 100 degrees. Come on, that's only boiling temperature of water. And it goes in the opposite direction. So read my lips. There is no correlation between R and S and plus and minus, dextrorotatory and levorotatory. Okay? By the time I'm done telling you this, 10 times, you'll never forget it. You'll remember that for the rest of your life. Okay? There's no difference between, or there's no correlation between the two. Just in the interest of fun, right? I like to have fun sometimes. Organic chemistry fun. Let's see, we got 1 here, we got 4 here, we got 2 here, we got 3 here. So this goes from 1 to 2 to 3. So good, it's S, good. So normally the way I do it is I draw a line from the carbon and then I put the line. Anyhow, just checking. Make sure there's no mistakes in here. Oh man, why did I switch slides? Can I ask you guys a question? And this is a totally honest question. What do you think would happen if you had a 50-50 mixture of an R and an S enantiomer? How do you think it would rotate plane polarized light? And it's not a trick. You had a 50-50 mixture of R and S. Anybody guess what would happen? Yes. Byron says no rotation. Skylar says wouldn't rotate. Alexa said it wouldn't. Lauren, Jonathan, you're all right. You're all 100% correct, right? Because if you think about it, if you have a 50-50 mixture of these enantiomers, one rotates it in this direction and the other one rotates it an equal amount in the opposite, they cancel each other out and you get no rotation. When you have a 50-50 mixture of two enantiomers, okay, we call that a racemic mixture, okay? It is a word that's going to come up. Racemic just means a 50-50 mixture of two enantiomers. And what happens is that they both rotate plane polarized light. Hell yeah. Yeah, they totally do. But they cancel each other. Okay, they just cancel each other out. Okay. Now, another situation is, well, what if it's not a 50-50 mixture, but what if it's not 100% one enantiomer over another? Then it's called having one enantiomer in excess. We call that Enantiomeric Excess. Then it has optical rotation, but it's going to be less than the pure enantiomer by itself. I'm not really going to ask you anything about Enantiomeric Excess, okay, on your quiz on Monday, okay? So you can take that to me. If I ask you a question about it, you write me an email and say, give me my point back. This would be on you said you wouldn't. I'm not going to ask you about Enantiomeric Excess, so I'm not going to cover it right now. What you need to know from section 5.4, okay? So there's two people at the university that teach this class, me and Dr. Anderson. And we both agree that the only things that you really need to understand from chapter 4 are the major points are these three things right here, okay? You need to understand what plane polarized light is. You should understand how the polarimeter works, right? You shine the plane polarized light. through a chiral compound, it's going to rotate plane polarized light. If it was the enantiomer, it would rotate it in the equal and opposite direction. You will see that in our textbook, and I didn't assign these questions, there are some questions where you're asked to do calculations where you would literally need a calculator. Okay, it's not like math spec where you can just add and subtract. Okay, you would need to have a calculator. You will not be asked to do those problems. Okay, however, you should know the terms what optically pure means. That means you've got 100% one enantiomer. You should know what enantiomeric excess means. It just means you've got one enantiomer in a greater amount compared to the other. And you should know what racemic mixture means, right? It's a 50-50 mixture of enantiomers, okay? Those are the main concepts that you need to take away from section 5.4. Okay, now we're getting close to the end of the lecture here, and I don't want to get into a ton of section 5.5 in the last 5 minutes. So let's see, we got to cover section 5.5, 5.6, 5.7 next class, and 5.11. Yeah, so we got plenty of time. But I want you to think about one more concept before we get together on Friday. And that's that we've talked about isomers way back in chapter 1, even in Gen Chem, we discussed constitutional isomers. Today, we talked about stereoisomers, and then we spent quite a bit of time talking about enantiomers, right? Non-superimposable mirror images. Well, if you're really astute, and this is not an easy thing to do, but you probably realize, like, hey, Mr. Dion, what if I have a compound, like, remember that compound we looked at today that had 5 chiral centers? Well, what if I had, you just kind of mixed up the chiral centers, and you had 2 compounds that are not enantiomers, okay, but they're not the same? How would you describe those 2 compounds? And the answer is you would describe those as diastereomers. Now, a better definition is compounds that are not superimposable, but they're not mirror images, okay? I would recommend that you commit these 2 definitions to memory for now, okay? I would ask you to memorize these 2 definitions. Why? Because when you step into the quiz on Monday, if you have the definitions memorized, it will just give you that confidence that you need to say, okay, well, I remember the diastereomers are stereoisomers that aren't mirror images. Then you can start looking and deciding, okay, are these mirror images or are they not, right? Then you can start making those decisions. By the time this class is done in May, trust me, you will know the difference between an enantiomer and a diastereomer, but I've taught the class enough to know that it's kind of handy to memorize the definition at the beginning, okay? Even if I ask you in organic 2, I'm like, hey, what's a diastereomer? And you're like, well, let me think about it. If I show you 2 diastereomers in organic chemistry 2, 99% of the time the students are able to tell the difference between them. Now, let's look at 2 simple examples of diastereomers. We looked at these 2 molecules earlier today when we were talking about cis and trans alkenes. Why the hell would these 2 molecules be diastereomers? Well, simple as this. They're stereoisomers, aren't they? We talked about that already today. We both said cis and trans are stereoisomers, but they aren't mirror images, are they? Right? If I have a mirror plane here, they're definitely not mirror images. So by this tasty, beautiful definition right here, okay, these 2 molecules, by that definition, they are diastereomers of each other. Okay? Again, we said that enantiomers have the same physical properties, boiling point, melting point, etc., but diastereomers are going to have different physical properties. Okay? Different physical properties. Anyhow, with that in mind, I think we're going to call it a day for there. And it's not like me to end class 2 minutes early or 60 seconds early, a whole heck of a lot.